Hello class, welcome to the Stat 215 Lecture 23 video. In this video, we are going to focus on two objectives. First, conducting a hypothesis test for the difference in two population means. And second, conducting a hypothesis test for the population mean difference. Let's begin by examining our first objective. We may recall the steps to the hypothesis testing. A hypothesis test is a standard procedure for testing a claim about a population parameter. Step 1, we state the hypothesis. Step 2, we specify the model and check the assumptions. Step 3, perform the mechanics of the test. Step 4, state our conclusion in the context of the problem. Now we can look more specifically at comparing two means. Previously, we used a one-sample z-test when sigma was known and a one-sample t-test when sigma was unknown to compare the population mean mu of one sample to a fixed value mu naught. Now we want to compare the means of a quantitative variable for two different populations. For example, the mean resting heart rate for men compared to the mean resting heart rate for women. Or say the mean cholesterol level for people who take drug A versus the mean for people who take drug B. In comparing two means, we have two independent populations of interest. We each have two independent samples, one from each population. And we want to compare mu1 and mu2. And just as in before, we may or may not know the population variances or standard deviations. In this case, there's two of them, sigma 1 and sigma 2. If we know sigma 1 and sigma 2, we'll be performing a two-sample z-test. If we don't know sigma 1 and sigma 2, we'll perform a two-sample t-test. Let's begin by examining the sample t-test. Our parameter of interest is mu1 minus mu2. That is the difference in the population means for groups 1 and 2. The most common null hypothesis, and the only one we'll examine in this class, is the null hypothesis of mu1 minus mu2 equal to 0. Our alternative hypothesis is one of three options. First, we could have the two-sided alternative, which is mu1 minus mu2 does not equal 0. Or we could have any of the two one-sided tests, that is, mu1 minus mu2 is greater than 0, or mu1 minus mu2 is less than 0. Our test statistic, in our case where we don't know the population variances, but we assume they are equal. If you recall, we considered this to be the pooled case. Our test statistic will be t equal to x1 bar minus x2 bar, all divided by SP multiplied by the square root of 1 over n1 plus 1 over n2, where, as you may recall, SP, our pooled standard deviation, is equal to the square root of the quantity n1 minus 1, n quantity, multiplied by s1 squared, plus the quantity of n2 minus 1, n quantity, s2 squared, all divided by n1 plus n2 minus 2. And as we are dealing with a t statistic, therefore, we are following the t-distribution, and in this case, our t-distribution will have degrees of freedom n1 plus n2 minus 2. Now let's look at our second t-test case, where we don't know our population variances and we cannot assume that they are equal. This is also known as the unpooled case. In this case, our t-statistic will be y1 bar minus y2 bar, all divided by the square root of S1 squared divided by N1 plus S2 squared divided by N2. And we will have a degrees of freedom as follows. The quantity of S1 squared divided by N1 plus S2 squared divided by N2, that entire quantity squared, divided by the quantity of S1 squared divided by N1 quantity squared, divided by the quantity of N1 minus 1, plus the quantity S2 squared divided by N2 quantity squared, divided by the quantity of N2 minus 1, N quantity. Now we can talk about calculating the p-value. So assuming that the null hypothesis is true and the assumptions are met, we will use the t-distribution to calculate the area as extreme or more extreme than our test statistic. Our steps for this are to draw a picture, and then we can use StatCrunch to allow us to select the alternative hypothesis, and it will display for us the corresponding p-value. We may be required to use the complement rule or add p-values and tails together for paper and pencil questions. As we have previously, we will use our p-value to make a statistical decision, meaning we will either reject or not reject the null hypothesis. As before, and with all hypothesis testing, we compare our p-value to the level of significance alpha. If our p-value is less than or equal to alpha, we will reject our null hypothesis. If it is where p-value is greater than alpha, we fail to reject the null hypothesis. Depending on whether we reject or fail to reject our hypothesis, we will then write the appropriate conclusion that will go along the lines of, at the, whatever our alpha level is, level of significance, we will either do or do not have sufficient evidence to conclude whatever our alternative hypothesis can say. This is an important thing to know and might be good to write down in your notes. This is the general form of writing a conclusion when we are concluding, yes, a hypothesis test. Let us talk about the assumptions we need for independent samples of t-test. First, we need to have each sample to be a random sample. These samples must be independent of each other, and each of these responses has to have a normal distribution. You must use two Q-plots to test this assumption, one for each sample. If the assumption is not satisfied for either sample or both, the inference will still be valid due to the central limit theorem as long as the sample size for the affected sample is sufficiently large. Okay, so now that I've thrown a lot of information at you, let's start looking at an example. A total of 38 college freshmen were administered to the Survey of Study Habits and Attitudes, SSHA, a psychological test designed to measure motivation and attitude towards study habits in college students. The 38 students were a simple random sample of which 18 were female and 20 were male. It is known that scores on the SSHA may explain success in college. Scores on the test range from a low of 0 to a high of 200. School administrators are interested in whether the population mean score for females is higher than the population mean score for males. We will let our alpha equal 0.05, and we will not assume equal population variances. This means this is the unpooled case. To begin, let us define our parameters of interest. We will let mu1 be the population mean SSHA score for females, and let mu2 be the population mean SSHA score for males. This means our hypothesis will be as follows. The null hypothesis will be mu1 minus mu2 equals 0. The alternative will be mu1 minus mu2 is greater than 0. Now, to think about this logically, because you may be wondering, where is that greater than coming from? Or how do we know for sure it's greater than? Well, we let our mu1 be females and our mu2 be males. In the problem, it said it wanted to test if the females were greater than the males. If we rearrange this equation, we would have female minus males is greater than 0. Now, if we plug in for our mu's, we know mu1 represented the females and mu2 represented the males. This is an alternative way to come up with the alternative hypothesis if you're struggling with it a bit. Next, we can check our assumptions. In the problem, it stated that each sample was a random sample, and obviously, our samples are independent. Now we need to consider whether each population of responses has a normal distribution, meaning, are the SSH scores normally distributed in the population of females and in males? Well, if we take a moment and look at a QQ plot in StatCrunch, we can see that both of the QQ plots are acceptable. They're not perfect, but remember, when we're using our normality assumption, you're rarely going to find that perfect case where that diagonal line is going to be followed exactly. So general rule is it close enough? And yes, it appears to be. So now let's conduct our independent t-test. One method of doing this is in StatCrunch. If we load the problem, we will have our data into two columns, one for each of our groups, male and female. Using StatCrunch, we can go to Stat, T-Stats, to sample with data. For there, sample 1 would be our female scores, sample 2 would be our male scores. If you recall previously, we had our calculation options. Pooled variances is when we assume our population variances are equal. That was not the case in this problem, so we need to leave it unchecked. When we did this previously, our stat to sample t-test, we were looking at it in the terms of a confidence interval. Now we're doing the hypothesis test. So we'll leave the default option of hypothesis test checked, and we will need to plug in the value that comes after our equal sign, in this case 0, and then the appropriate alternative hypothesis. We may select some optional graphs and tables if we desire, such as the summary statistics or the QQ plot that we saw above. If it's not required, you don't need to do so. Let's continue. So if we were given our sample statistics, we would see that we have a mean for the females of 1.41 approximately and a standard deviation approximately of 26.44. The male scores have an approximate mean, or actually exact mean in this case, of 121.25 and an approximate standard deviation of 32.85. We can see that the sample mean for females is greater than the sample mean for males. But just because the means appear to be different, that doesn't mean we have enough evidence to truly say that the population mean for females is greater than the population mean for males. Instead, we need to conduct our hypothesis test to say for sure. Once again, we can recall that mu1 is the mean of the female score and mu2 is the mean of the male score. Mu1 minus mu2 is the difference between. We have selected in our StatCrunch the appropriate hypothesis, and we did not check pool variances. We then could click Compute, and we can be given the following hypothesized results. We were given our sample difference, our sample standard error, our degrees of freedom, our t-stat, and our p-value. This p-value is important because we can use it to make our conclusion. Since our p-value is equal to 0.0236, which is less than 0.05, this implies that we can reject our null hypothesis. So now we can actually say that at the 5% significance level, there is sufficient evidence to conclude that the population mean SSHA score for females is higher than the population mean SSHA score for males. At this point, let's take a look at examine some more p-value calculations. Specifically, let's take a look at the case where we have the two-sided alternative. One way to calculate this would be to calculate the one-sided test. And as you can see from the visual, the left and the right side are equivalent. So if you were just to calculate one side, you could multiply by 2 to get the whole p-value. This is the method I recommend. An alternative way is if you select the between option in StatCrunch. The between option will give you the area of the center, and you can use the complement rule and do 1 minus to find the tails. Either option is acceptable. It is completely up to you. Okay, now let's take a look at our third alternative hypothesis, where mu1 minus mu2 is less than 0. This is the left tail test. In this case, our test statistic is still going to be the 2.0563, as we can see in our graph. If you use StatCrunch, it will give you our p-value of 0.9764. An alternative method of doing this would be to use the p-value we already calculated and realizing this is going to be its complement. So you could do 1 minus 0.0236. Either option is acceptable, but use the one that you're more comfortable with. Okay, so at this point, let's take a look at example 2. As soon as I change colors to something that's not that bright green. All right, we have a random sample of 31 females, group 1, representing a population of females, and a random sample of 47 males, group 2, representing a population of males. We have the IQ of each subject. Is there a difference, on average, between the population mean IQ scores of males and females? Let alpha equal 0.05. We do not assume equal population variances. Okay, so now to begin, let us define our parameters. Let mu1 equal the population mean IQ for females. Let mu2 equal the population mean IQ for males. Our alternative hypothesis will be the same as it was, our null hypothesis will be the same as it was in our previous problem. Mu1 minus mu2 equals 0. What will be different is our alternative hypothesis, which will be mu1 minus mu2 not equal to 0. Remember, in this question, we weren't given an indication of direction. We just wanted to know if there is any difference, less than or greater than, between males and females. To do this in StatCrunch, after it's loaded, we can go to Stat, T-Stat, ToSample with data. Remember, a lot of questions in your homework and practice will probably give you the data as a summary, meaning it'll let you know what the means and standard deviations are. That's okay. That's easy to plug in. Once we select the correct options and calculate the correct hypothesis test, we can select our optional graphs and tables, selecting our p-value plot, our summary statistics, and our QQ plot. Make sure you don't check pooled variances because we were told not to assume that. After we hit compute, we will be given our QQ plots that will give us the opportunity to examine and check our assumptions. We were given that each sample was a random sample. We are assuming that the samples are independent of each other. Looking at the plots below, I would say that we're okay on our normality front. So this means we can go ahead and examine our results. We can see from our sample statistics that we have a sample mean IQ for female of 105.84 and a sample mean IQ for males of 110.96. Okay, so right from the appearance, it looks like males have higher IQ. But does that mean we have sufficient evidence to say that males and females have different IQs? Well, just looking at the means isn't enough. We have to go through the whole test. So by examining the test results, we are given our sample difference, our sample standard deviation, our degrees of freedom, our t-statistic, and our p-value. Remember that p-value is really, really important because it's what we're going to use to make our determination. So since our p-value is 0.1057, which is clearly greater than our alpha level at 0.05, we do not reject the null hypothesis. This means at the alpha equals 0.05 level of significance, we do not have sufficient evidence to conclude that the population mean IQ for females differs from the population mean IQ for males. Now I want to draw you back up a couple slides where we were given the mean differences. So you can see clearly in this sample, the males had a higher IQ for females. What our results said is this difference of our 5-point difference approximately of IQs wasn't definitive, wasn't conclusive enough to actually say that there is a difference between male and female IQs. This small of a difference could be attributed to various errors, luck, randomness, etc. Okay, let's go back to what we were looking at before. All right, finishing off our example 2 with more information with our p-values. So we do want to take a quick moment and make sure we understand how to calculate when we have various alternatives. So for example 2, our original alternative hypothesis was not equal to. If we examine the situation where it was less than 0, our t-statistic and degrees of freedom would remain the same. But if we are interested, we could go into the t-calculator, plugging in the degrees of freedom and the appropriate test statistic, having less than, enter, and we can get our one-sided p-value. Okay, now let's take a look at using the summary statistics in StatCrunch. As I mentioned previously, a lot of your homework problems are going to give you summary data, not necessarily the raw data. So if you go to T-Stats, TOSample, and Summary, this is the screen that's going to pop up. As you can see, it'll have under sample 1, sample mean, sample standard deviation, and sample size. You just need to plug in that correct information for the first sample and the correct information for the sample 2. Be careful. A lot of times problems give you your sample size first and then the sample mean. So just make sure you're reading carefully because sometimes it's just habitual to write the first number you read first and so on. Also be sure that you check the pooled variance option when appropriate. So when you're told to assume the population variances are equal, you should go ahead and select the pooled variance option. Okay, so this brings us to our second objective. Conduct a hypothesis test for the population mean difference. So when we're dealing with a paired samples t-test, It is when we have two sample t-tests assumes that the groups are independent. However, in this case, what if we measure the same individuals twice? Well, in that case, we have matched pairs. So this means we are interested in the population mean difference, mu d. You may recall talking about paired samples when we did confidence intervals. If you recall, we let d equal our difference. Our null hypothesis when we are doing paired t-test is going to be mu d equals 0. Our alternative hypothesis will be mu d not equal to 0, mu d greater than 0, or mu d less than 0. Once again, 0 does not always have to be the case, but in this course, you're just beginning to learn this, so we're going to stick to 0. When we don't use 0 is when we have an established difference that we're trying to equalize for. Let's keep going and examining our paired t-test statistics. So d bar is going to be our sample mean of difference, SD is our sample standard deviation of the differences, n is our sample size, as always. Our test statistic is going to be d bar minus 0, all divided by SD divided by the square root of n. As you saw that says t equals, that means we're using a t-distribution, in this case with n minus 1 degrees of freedom. And if you have noticed, this is identical to the one sample t-test. Same how the paired t-test was identical to the one sample t-test. Our column of data that we're interested is the column of our differences. Our p-value will be calculated using the t-distribution with n minus 1 degrees of freedom. We will, as always, make a statistical decision by comparing p-value to alpha, and we will write our conclusion in the context of the problem, in this case about our population mean difference. Now it's important to talk about the assumptions. We have two major assumptions that we're interested. One, that we have a random sample of differences, and that the population of differences has a normal distribution. Remember, we can check this using a QQ plot. Let's begin by taking a look at a paired t-test example. During the fall semester at Penn State, one brave researcher asked a random sample of 119 female students how much they weighed. These women reported their actual weight and then also answered the question, "What is your ideal weight?" The researcher suspects on average actual weight is greater than the ideal weight in this population of college women. We will let alpha equal 0.05. Now if we take a look at the data, we have a column of our actual weight, the ideal weight, and the difference. Notice in this case it was actual minus ideal. Just to be clear, that this is a paired t-test, we can see that we have two weights for each student. We define the difference, as I said before, as actual minus ideal, which will imply that our parameter mu d is going to be the population mean difference in weight. And we want to know, per the question, if actual weight is more than the ideal weight, meaning our null hypothesis will be mu d equals 0, and our alternative will be mu d greater than 0. If we scroll up, we can see, as a rule, the differences are either 0 or positive. This makes me think that I should expect to reject our null hypothesis, and our alternative hypothesis that actual is going to be greater than the ideal weight is probably going to be true. But let's check for sure. Okay, so we're going to check the assumptions now. We know that the sample was taken at random, and we want to know, are the differences normally distributed in the population? Well, looking at the QQ plot, I would say this is not great, to be honest. I would probably say that there's a problem with this, looking at it. However, as we've discussed previously, if our sample size is large enough, the central limit theorem kicks in, and if I recall, we had quite a large sample size of 119 students. So even though this isn't a great QQ plot, I'm going to go ahead and say that it is appropriate to use our pair t-test. Everything I just said is written on slide 46, just in case you didn't believe me. All right, so now let's actually calculate our pair t-test. If we want, we can use StatCrunch to make it easier. We'll go to Stat, t-stats paired. Since we've defined the difference to be actual minus ideal, we need to remember that actual will have to be sample 1, and then ideal is going to be sample 2. Be careful not to switch this up because it can affect your results. Then we will need to select the hypothesis test, which should be there automatically, and then adjust for the correct alternative hypothesis. We may choose to select our plots shown in our two-sample test, but that's up to you. Assuming that you do, though, you can see that the sample statistics for actual versus ideal, we have our means and our standard deviations. We can see that the sample mean weight for the actual weight is 132.78 pounds, and the sample mean ideal weight is 122.13 pounds. We see a sample mean difference of 10.65 pounds. Given the results above, does that mean we have sufficient evidence to say, on average, actual weight is greater than ideal weight in the population of female students at Penn State? Meaning, do we have sufficient evidence to say the population mean difference is greater than 0 when the difference is actual minus ideal? Well, based on the results above, it leans that way, but we actually can't definitively say that. We have to do the test. So by looking at our test results, we have our mean difference, standard error, degrees of freedom, test statistic, and the all-important p-value. Notice this p-value is less than 0.0001. If we desire, we can look at our visual for this. As it is a one-sided t-test, we can see that our shaded area is way over here. That makes sense because our p-value was less than 0.0001. And since that's the case, and it is clearly less than 0.05, we strongly will reject the null hypothesis. This means at the 5% significance level, we have sufficient evidence to say that the population mean difference in weight, where difference is actual minus ideal, is greater than 0. Meaning, we have sufficient evidence to say that on average, actual weight is greater than ideal weight in the population of female students at Penn State. Wonderful. That brings us to the end of this lecture. Let's just talk about what we've learned so far. So we learned that we can use our standard hypothesis testing procedure to look for differences between means of groups. And when observations are measured twice, we are interested in hypothesis testing for the population mean differences. All right. Have a good night, everyone.